I want to begin with a confession. When I was a boy in Far Rockaway, I used to lie on my back in the summer grass on hot nights and stare up at the sky, and I would get this funny feeling in my chest, this strange electric feeling, because I was absolutely certain that someone was looking back. Somebody on one of those pinpoints of light, lying in their own strange grass, under their own strange sun, looking at our sun, which to them is just another star, and feeling the very same thing. And I thought, one day, we will meet them. Maybe not me, maybe my grandchildren, but someone will meet. Well, I grew up. I studied a little physics. And I'm going to tell you something tonight that I still don't quite know how to feel about, even now, after all these years. I'm going to tell you why we will never meet them. Not probably won't. Not it's going to take a long time. Never. And I don't mean never for the boring reasons that civilizations are rare, that they blow themselves up, that we just happen to be unlucky. No. I mean never. Because the universe itself, the fabric of space and time, the laws of matter and motion, the deep rules of the thing we live inside of the universe, has quietly, politely, without any malice at all, locked the doors between us. Now here's the part I love. Here's the part I want you to stay with me for, because I can already see some of you leaning back with your arms crossed. The reason is more beautiful than any flying saucer story. It's more astonishing than any government conspiracy. It's written right there in the physics, and once you see it, you can't unsee it, so let me show you. Let me start with a lunch. In the summer of 1950, up at Los Alamos, where I used to work, during the war, 4 physicists were walking to the cafeteria together. Enrico Fermi, Edward Teller, Herbert York, Emil Konopinski. I knew Fermi. Fermi was the real thing, a beautiful mind, you know, the kind of fellow who could estimate anything on the back of a napkin and come out within a factor of 2 of the right answer. So the 4 of them are walking and they're joking about the flying saucer reports in the newspapers. There were a lot of those back then. Everybody was seeing saucers. The conversation wanders off to other things, the way conversations do. And then they sit down to eat. And halfway through lunch, Fermi, apropos of nothing, looks up and says, "But where is everybody?" And everybody at that table knew exactly what he meant, because they'd been doing the arithmetic in their heads all morning. The galaxy has something like 100 billion stars. It's more than 10 billion years old. Even if intelligent life is rare, really, really rare, and even if spreading out into space is slow, 10 billion years is a long, long time. If just one civilization, 1 out of 100 billion stars, had set out 100 million years ago at 1/10 the speed of light, they would have colonized every corner of the galaxy by the time the dinosaurs were getting started on Earth. One civilization, 100 million years, that's a blink, cosmically speaking. So where are they? Why is the sky silent? Why does nobody knock on our door? For 75 years now, people have been trying to answer Fermi's question. And most of the answers are depressing. Maybe civilizations destroy themselves. Maybe biological intelligence is freakishly rare. Maybe they're hiding from us. Maybe we're in a zoo. You know, I don't buy any of those. I don't buy them because I've looked at the physics, and the physics itself gives an answer so much stranger and so much more interesting than any of the clever speculations. The physics says it doesn't matter how many of them there are. It doesn't matter if there's a civilization on every 3rd star. They can't get here, and we can't get there. Not ever. Why? Let me show you why. And to show you why, I have to do something that's surprisingly hard, which is to make you really feel how big space is, because you think you know. You've seen the Hubble pictures. You've heard the word light year, but you don't feel it. Nobody feels it. Our brains didn't evolve for this. Here, try this with me. Imagine the sun is a grapefruit, a nice big grapefruit, sitting right here on the stage. On that scale, where is the Earth? The Earth is a grain of sand, about 15 yards away. You could hit it with a rock. And Pluto, way out at the edge of the solar system, Pluto is a smaller grain of sand, about half a mile away. Okay? That's the whole solar system, all of it. The entire neighborhood we've ever sent anything to, a grapefruit and a few grains of sand spread over maybe a mile. Now, where's the nearest star? On this scale, the nearest star, not a distant star, the nearest one, Proxima Centauri, is another grapefruit about 2,500 miles away. That's roughly from New York to Los Angeles. So picture it. Grapefruit here in this room, grapefruit in Los Angeles, and between them a few grains of sand, and otherwise nothing. Nothing at all. For 2,500 miles of empty. That's the density of stars in our neighborhood. That's the sparsest, loneliest thing you've ever imagined, and it happens to be the actual universe we live in. And Proxima is the closest. The rest of the galaxy is farther. The center of the galaxy is 26,000 light years away. Andromeda, our next-door galaxy, is 2.5 million light years. And the observable universe is about 46 billion light years across in every direction. 46 billion. You hear these numbers and your brain sort of glazes over, doesn't it? That's because your brain is smart enough to know it cannot handle them. Your brain evolved for catching rabbits, not this. So, given this appalling vastness, how do you get from one place to another? Well, let me tell you what we've actually done. The fastest thing we have ever launched into space is a little probe called Voyager 1. We sent it out in 1977. It's now about 150 astronomical units from the sun, moving at about 17 kilometers per second. 17 kilometers a second! That's fast! That's 40,000 miles an hour. If Voyager were aimed at Proxima Centauri, which it isn't, but suppose it were, how long do you think it would take to get there? 73,000 years. Now let me put that in perspective. Human civilization, agriculture, cities, writing that's all about 12,000 years old. The pyramids are 4,500 years old, and they are already ruins. We are asking a machine made of aluminum and silicon and running on a plutonium battery to keep functioning for 6 times longer than all of human history. It cannot be done. No machine we have ever made lasts for 73,000 years. And that's just to the nearest star. You say, fine, we'll build better machines, faster machines. And this is where people always jump to, well, we just need to go faster. We'll go at the speed of light. We'll go near the speed of light. And this is where I have to break some news to you. And it's not news you're going to like. You cannot go at the speed of light. Not it's hard. Not we haven't figured it out yet. You cannot. And the reason you cannot is not a technological reason. It's a reason woven into the deepest layer of reality we know about. Einstein figured this out in 1905, and I still think it's the single strangest, most beautiful fact about our universe. The speed of light, we call it c, it's about 300,000 kilometers per second, is not really the speed of light. That's a bad name for it. Light happens to travel at that speed because light has no mass. But the real name for c ought to be something like the speed of causality. It's the speed at which any effect, any push, any signal can travel from one place to another. It is the maximum rate at which the universe allows here to influence there. Light travels at it because it has to. Anything with mass travels below it. And the gap between below and at, this is the part people miss, the gap is infinite. Literally, mathematically infinite. Here's how it works. When you push on something, it accelerates. Push twice as hard, it accelerates twice as much. That's what Newton told us, and for most of life that's true. But as the thing you're pushing gets faster, it gets harder to push. Not in the arms get tired way, in a way that is built into nature. The same push gives you less and less acceleration. And the closer you get to c, the harder it gets, until you're trying to push a thing that requires infinite energy to go 1 more meter per second faster. Infinite, not a lot, infinite. The universe has placed a signpost at that speed which says, you don't get to cross. Let me put numbers on it. Suppose you want to accelerate a spacecraft, let's say a tiny one, 1,000 kilograms, about the weight of a small car, to 1/10 the speed of light. That's 30,000 kilometers per second, 10%. The kinetic energy you need to do that is about 5 times 10 to the 18th joules. That's roughly how much energy the entire human species uses in a month. All of us, every car, every factory, every light bulb, for a whole month, just to push one small car to 1/10 of light speed, one way, no deceleration, no return trip, and 1/10 of light speed still takes 40 years to reach the nearest star. Not a round trip. One way. What if you want to go to 1/2 the speed of light? Now you need 12 times more energy. What about 99%? Now the energy has gone up by a factor of over 100. You need the total energy output of the sun for several seconds focused perfectly onto your little spacecraft and not a single drop wasted. And remember, you have to stop at the other end or you'll go shooting past your destination at half the speed of light. So you need to do it all over again to decelerate. And I haven't even told you the worst part yet. Because how do you carry that energy? This is the problem that drove Tsiolkovsky mad in the 1890s and every rocket engineer since. You have to carry your fuel with you, but the fuel has mass. And the more fuel you carry, the more fuel you need to push that fuel. It's a snake eating its own tail. The equation that describes this is called the rocket equation, and it has a little mathematical feature in it, a logarithm. That means the amount of fuel you need goes up exponentially with the speed you want to reach. Let me make this concrete. If you want to get a spacecraft to 10% of the speed of light using the best fuel humans currently know how to burn, chemical fuel, like what we launch our rockets with, the amount of fuel you need compared to the weight of your ship is a number with more zeros in it than there are atoms in the known universe. I'm not exaggerating. That's a real calculation. Chemical rockets cannot go to the stars. They physically, mathematically cannot. You could convert every atom in the solar system to rocket fuel, and you still couldn't push a teacup to Proxima Centauri at any reasonable speed. You say, okay, Dick, we'll use fusion. We'll use the fuel the sun uses, hydrogen fusing into helium. That's much better, because each fusion reaction releases about 10 million times more energy per gram than chemistry does. Great. With perfect fusion rockets, which we don't have. But suppose we did, you could maybe get to 10% of light speed with a reasonable mass ratio. Maybe. And you're still at 40 years per trip. One way, you say, fine, we'll use antimatter. The best possible fuel. When matter and antimatter meet, they annihilate completely. Every bit of mass becomes energy, according to Einstein's famous formula, E equals mc squared. 1 gram of antimatter reacting with 1 gram of matter releases roughly the energy of the Hiroshima bomb. Okay. Now at least the rocket equation is being kind to us. But here is a lovely but. In the entire history of human civilization, we have produced less than a nanogram of antimatter. A billionth of a gram. Total, ever, and each bit of it cost billions of dollars and vanished in microseconds. To fuel one interstellar ship to one nearby star, you would need to produce something like 100 tons of antimatter. 100 tons of the substance we currently produce a billionth of a gram of. Using, by the way, more electricity to make the antimatter than the energy you eventually get out of it. So that's problem one. The energy is against you, the fuel is against you, the mathematics very politely has told you no. But maybe you don't believe me. Maybe you say, Dick, physics always finds a way. We'll figure something out. We'll invent something clever. All right. Let me give you another problem. This one has nothing to do with engineering. This one is just about what happens when you go fast through space. Space isn't empty. You think it is. In the textbook picture, it's drawn as blackness between stars, but that's a lie. Space between stars has about 1 atom of hydrogen per cubic centimeter, sometimes more. Sometimes there are grains of dust. Very tiny grains, most of them just a few micrometers across, and you'd never see them in a million years at normal speeds. Now, at normal speeds, these things don't matter. You plow through them and nothing happens. But at high speeds, at relativistic speeds, everything changes. Everything. When you're moving at half the speed of light, a single hydrogen atom hits you with the energy of hundreds of millions of electron volts. That's the energy of a radiation particle from a nuclear reactor. And you're sweeping up, in a reasonably sized ship, you're sweeping up trillions of these atoms every second. Your ship is bathed in a hurricane of high-energy radiation that cooks every living thing inside, that destroys electronics, that tears molecules apart at the chemical level. You'd need meters and meters of shielding, which adds mass, which means more fuel, and now the rocket equation is laughing at you again. It's always laughing at you, this equation. But forget the atoms. Let's talk about a single dust grain. One tiny dust grain weighing 1 milligram smaller than a grain of sand, the kind of thing you wouldn't even notice on your fingertip, 1 milligram, moving relative to your ship at half the speed of light. The kinetic energy of that one collision is about 10 billion joules. That's the energy of 2 tons of TNT hitting your ship. And there are billions of these grains between any 2 stars. The galaxy is absolutely full of them. Your interstellar spaceship, however big it is, however cleverly designed, is not going to survive even one such collision, and it's going to encounter many. Space itself becomes a minefield when you try to move through it fast. So you say, fine, we'll slow down. We'll go at 1% of light speed to be safe. Now the dust problem is less bad, but now you're back to 1,000 years to reach the nearest star. 1,000 years. That's a civilization. That's generations of people born on the ship, growing up on the ship, dying on the ship, their grandchildren finally arriving only to find that while they were traveling, the people who sent them have long since forgotten they ever existed. The ones who boarded are not the ones who arrive. They're strangers, separated by centuries from the world that launched them, and this is just for the nearest star. Extend this to the whole galaxy, and you're talking about a 100,000-year journey, end to end. Civilizations don't last 100,000 years. Our own species has only existed in anatomically modern form for about 300,000. Our technological civilization is less than 300. You're starting to feel it, right? The physics is very patient. It just keeps saying no, politely, in a different way, each time you ask. And if you still don't believe me, I want to show you one more thing, and this one is the knockout. Because I've been talking about practical problems, energy, fuel, dust, time. Those are real, but they might feel to you like engineering problems, maybe solvable in principle. Let me now show you the thing that is not solvable, even in principle. Let me show you the deepest reason, the reason that is written into the bones of space itself. Einstein taught us that space and time are not separate things, they're woven together. And when you move fast, time for you slows down relative to someone standing still. This is not a trick. This is not an illusion. This has been measured. We put atomic clocks on airplanes, and they come back slightly behind the clocks on the ground. We accelerate particles in the big accelerators and watch them live longer than they should. Time dilation is real. It's the most beautiful thing in physics. Now, here's what this means for interstellar travel, and here's where it gets strange. If you could somehow get a spaceship up to 99% of the speed of light, forget for a moment all the energy problems at that speed, your time runs about 7 times slower than Earth time. So, in your reference frame, you could cross the galaxy in about 14,000 years of your own time. That's still long, but it's imaginable. At 99.9%, the factor is 22. At 99.99%, it's 70. Get close enough to light speed, and you could in principle cross the whole observable universe in a single human lifetime for you. But, and here is the knife, while you're doing that, the universe outside is aging by the full travel time. You cross the galaxy in 14,000 years of your time. The galaxy ages 100,000 years while you're gone. You come back home, and everyone you ever knew is 100,000 years dead. Their descendants, their civilization, it's all gone, replaced by something unrecognizable, if there's anything left at all. This is not a round trip, this is a one-way ticket to a future that doesn't know you. Relativity guarantees it. The faster you go, the more future you buy, and you cannot ever come back. So here's the picture for aliens. Suppose there is a civilization on a planet 1,000 light years from here. 1,000 light years is a drop in a galactic bucket. It's practically next door. They build their beautiful relativistic ship. They accelerate it to 99% of light speed. 9 of their years later, just 9 years of ship time, they arrive, but on their home world, 1,001 years have passed. The species that sent them is gone or changed beyond recognition. They arrive at Earth, and there's us, or our descendants, or more likely a cold ball where we used to be, but more to the point, there's nobody for them to report back to. There's no civilization to sustain an interstellar program. There's no them anymore. The whole idea of galactic empires, of communicating societies spread across the stars, it doesn't work because societies cannot hold together across those distances. The speed of light isn't just a wall. It's a divorce. It divorces any 2 points in space from each other, culturally, temporally, civilizationally. And you know what? That still isn't the deepest reason. That's still just a problem about civilizations. Let me tell you now, the thing that is written into the universe itself, the thing that no technology, no cleverness, no civilization in any conceivable future can get around. Not ever. The universe is expanding. Galaxies are flying away from each other. We've known this since Edwin Hubble in 1929 looked through his telescope on Mount Wilson and noticed that the light from distant galaxies was shifted toward the red. The farther away they were, the faster they were receding. That was the discovery of the expanding universe, and at the time we were all very excited about it. But here's the part people often miss. The expansion is not galaxies flying through space. The expansion is space itself growing. New space is appearing everywhere, between everything, all the time. Two galaxies sitting perfectly still in their own patches of space are nonetheless getting farther apart from each other because the stuff between them, space itself, is getting bigger. And here's the strange, wonderful, terrible part. Space doesn't obey the speed of light rule. Space itself can expand as fast as it wants. Two galaxies, sufficiently far apart, can be moving away from each other faster than the speed of light, because it's not that they're moving through space, it's that the space between them is growing faster than light can cross it. And that means that light leaving one of those galaxies will never, ever reach the other one. Not in a trillion years. Not in a Google of years. Never. The space between is outpacing the light. This isn't science fiction. This is measured. Cosmologists have worked out something called the cosmological event horizon. It's the sphere around us right now with a radius of about 16 billion light years, beyond which anything has already fallen out of contact with us forever. Galaxies beyond that boundary, and there are an awful lot of them can never send us any signal that we could possibly receive. Not because of any technological limit, because the space between us is stretching faster than any signal they could send. And it's getting worse. The expansion is accelerating, thanks to something we call dark energy, which is maybe the dumbest name we've ever given to anything in physics, because it just means we don't know what it is. But whatever it is, it's causing the expansion to speed up, which means every moment more galaxies cross our event horizon and are lost to us forever. Each year, roughly 20,000 galaxies redshift out of our observable reach. They don't vanish. They just fade, redden, slow down, and finally they're just gone. Not visible, not reachable, not signalable. Gone. Here's a number that took my breath away when I first did the arithmetic on the back of a napkin. Of all the galaxies we can see in the sky today, and we can see hundreds of billions of them, about 97% are already unreachable. Even if we built a spaceship right now that could travel at exactly the speed of light, and we launched it today, 97% of the galaxies we can see are already receding from us, faster than that ship could chase them. We can watch their light arriving from their past light that left them billions of years ago, but we could never, ever catch them. They are, for all practical purposes, in a different universe from ours. And I want you to sit with that for just a moment. Don't shake your head. Stay with me. All those galaxies, all those hundreds of billions of stars in each of them, all those possible planets, all those possible civilizations that may have risen and fallen across cosmic time. Already, right now, as we sit here in this hall, they are beyond any possible contact with us. Not hard to reach. Not it'll take a while. Gone. The door is closed. It has always been closed. It closed long before we were born because of a decision made by the universe itself quietly, in the first tiny fraction of a second of its existence, about how fast space would be allowed to stretch. And this is why I say, this is why I'm telling you tonight, we are not going to meet them, and they are not going to meet us. The universe is not built for it. It never was. Any civilization in our own galaxy, if there are any, is separated from us by time and by energy and by dust and by the brutal arithmetic of the rocket equation. Any civilization in our neighboring galaxies is separated from us by all of that, plus millions of years of light travel. And any civilization beyond that is separated from us by an expansion they cannot cross, any more than you can cross a river that flows faster than you can swim. The locks are all thrown, the boundaries are all up, and the funny thing is, the universe was never hiding them from us. The universe was never being cruel. The universe was just doing its own thing, expanding according to its own laws, and we happened to be little creatures with little lifespans on a little rock looking up at it. Now, I could stop here, and I could send you home sad. Some people, when they hear all of this, get sad. They say, Dick, you've taken the romance out of the sky. You've taken the dream away. And I understand that. I do. I was that boy in Far Rockaway, too, you know. I was that boy who thought someone was looking back. And it hurts a little to learn that they probably were, and they probably are, and we are never, ever going to touch. I don't want to pretend that doesn't hurt. It does. But I want to tell you how I've come to think about this, because I think, and this is just me now, this is not the equations, this is the old man talking, I think there is something extraordinary to be taken from it. And I don't mean as a consolation prize. I mean as a revelation. Consider the fact that the universe is so vast, so old, so full of the possibility of other minds, and consider the fact that we can, from our tiny perch on a grain of sand orbiting a grapefruit in the thin slice of one of hundreds of billions of galaxies, figure all of this out. We can sit here in this room on a Tuesday night and know where the cosmic event horizon is. We can calculate the energy required to reach the nearest star. We can look at a photograph of a galaxy 10 billion light years away and understand that its light has been traveling toward us since before the Earth existed. We can do this. We can know this with no bigger apparatus than a 3-pound lump of meat inside our skulls and a few good pencils and a few good arguments between us. That, to me, is the astonishing thing. Not that we're alone. We probably aren't alone in the sense of the universe being barren of minds. The arithmetic suggests the opposite. We're alone in the sense of being unmeetable, but we're not alone in the sense of being unable to know. We can see across the event horizon, backwards in time, all the way to the beginning of everything. We can know that other minds may exist, can reason carefully about what they would see if they looked at us, can write equations that apply equally to them. The universe has made it so that we cannot meet, but it has made it so that we can understand. And understanding, it seems to me, is a deeper form of contact than meeting is. You don't understand your neighbor just by bumping into him in the driveway. You understand him by thinking carefully about what it's like to be him. And in that sense, in the deepest sense, we are in contact with every conceivable civilization in every corner of every unreachable galaxy. Because we've thought about them. And if they're out there, they've thought about us. And the thinking is the real thing. The meeting would have been the illusion. So the next time somebody tells you they saw a flying saucer and somebody will, there's one every week in the papers, smile a little, be gentle with them. But know that you've been let in on a better secret than they have. The real story of life in the universe is not a story of visitors from beyond. It is a story of trillions upon trillions of stars scattered across hundreds of billions of galaxies, separated from each other by distances that light cannot cross in the age of the universe, filled perhaps with countless minds. Each one, just like us, in one profound respect, each one locked in its own little neighborhood, looking out, wondering, and maybe this is the thing I want to leave you with, the thing I want you to take home tonight. Maybe the universe is not quiet because nobody is out there. Maybe it's quiet because everybody is. Maybe every civilization at some point figures out the physics, realizes what I've just told you, and understands that the right thing to do is not to shout across a canyon that has no bottom and no other side. Maybe the right thing in the end is simply to look up the way we are all looking up now, and to wonder, and to know that somewhere out there, someone else is doing exactly the same thing, knowing they will never know us, and loving the knowing anyway. The sky is not empty. It's full of company we will never meet, and that, it turns out, is even more beautiful than the other thing would have been. Because if you ever wondered whether the universe was designed to break your heart, well, it was. But it gave you, in exchange, the capacity to understand that it was. And that, let me tell you, is not a bad trade. That is the best trade anyone ever made. Look up tonight on your way home. The stars will be there. The light hitting your eyes left them years ago, some of it centuries ago, some of it before the pyramids were built. It's old light. It's tired light. It crossed all that emptiness to find you. And it brought a message not from anyone in particular, not from any civilization, a message from the universe itself. And the message is this: I made you capable of knowing me, even though I would not let you visit, even though I would not let anyone visit you. I gave you this. I gave you the looking up. Go and do it.